All right, so section 3.2, proving theorems. So we got a couple kind of just like background knowledge since we skipped over chapter 2. Just want to make sure we remember these symbols for subsets, unions, and intersections. Then we have two types of proofs on this particular section. That's direct proofs and proofs by contradiction. So as I mentioned in section 3.1, we will essentially tell you how to solve these proofs, like which method to use. So there's not going to be like, we're going to be like, which method should I use? It'll kind of always be specified. All right, so subsets, quick definition provided by mathisfun.com. A is a subset of B when every member of A is a member of B, and that's read as A is a subset of B. So that means like you have all these guys right here. So B is all the blue stuff. B is 1, 2, 3, 4, 5. A is 1, 2, 3. So A is a subset of B. We have union. The union of two sets A and B is a set of all elements which are either in A or in B. So union is an or statement. That's kind of a cool thing just to kind of remember about these. If you don't, remember that is a union is or. So it's in this or in that. So it's like in both. And so if A is 1, 2, 3 and B is 3, 4, 5, then it's just all of it. And then intersection is the opposite. Intersection is an and statement. So intersection is going to be an and statement. And so in this case here, the intersection of two sets, A and B, is a set of all elements which are in common in A and in B. And it's read as A intersects B. And so we can see here that in this case, PQM is our intersection. So that's what they have in common. So that's our intersecting set. And those two are provided by mathonly.com. All right, so direct proofs. A proof in which we begin with the assumption that the hypothesis is true, and then use the hypothesis and definitions in previously proved theorems and mathematical reasoning to argue the conclusion. So what I want you to kind of take away from that is like thinking about the fact that it's like these are the things that we'll use. We'll always start with the hypothesis, then we'll follow it by some definitions, and then we'll maybe like pull like some previously proved theorems, and then any kind of mathematical reasoning, like algebra stuff or whatever it be, to be able to argue that we can get to the spot where we can show that the conclusion is actually true, and that would be called a direct proof. So our first proof we're going to look at is direct proof. Using direct proof is suppose A, B, and C are sets. If A is a subset of B and B is a subset of C, then A is a subset of C. So to kind of like think about this, one really kind of like way to kind of help us is like, let's like set up some like, these aren't arbitrary necessarily. I mean, they're kind of, but they're just like saying, okay, we have this P and this Q. We don't really know what P and Q are. So they are arbitrary, I guess. Sorry about that. So A is PQ, B is PQR, and C is PQRST. So according to this, A is definitely a subset of B because in A we have P and Q, and B we have P, Q, and R. So let's just get my marker out here. So we've got this guy. Oh, that'll work. Nah, that's dumb. So we've got P and Q, and then P and Q. So A is definitely a subset of B, check. And then we go, is B a subset of C? So B has P, Q, and R. C has P, Q, and R. So check, B is a subset of C. So then with these arbitrary numbers, we check all the way, and we can see that PQ is in C. So check, A is definitely a subset of C. And so in such circumstances, must it always follow that A is a subset of C? Well, how do you know? Look carefully at individual elements. So let's say if P was an element of A, and since A is a subset of B, what does it say about P? Well, it's saying that P has got to be in B. And since B is a subset of C, that means that P would have to be in C also because P was in A, which is a subset of B, and it has P, and P is a subset of C, so therefore we can move our way through and say that. So it's important for us to think about those definitions. So kind of going through, so we've got our hypothesis, and then we're going to follow up with some definitions and maybe some previous theorems. Since this is a theorem about the relation of a subset, we must give careful attention to this definition. X is a subset of Y if and only if each element of X is an element of Y. That's our basic definition of subset. So our reflection here is going to be, we are trying to show that A is a subset of B, B is a subset of C, therefore A is a subset of C by showing that an element of A is also an element of C. Follow our definitions. If we let A be an arbitrary element of A and argue that it must be an element of C, we will be done. Hence the first statement in our proof, let A be an element of A, of set A. We will then look carefully at our hypothesis. A is a subset of B, B is a subset of C, to see whether we can show that A is in C. So all of that preparation for this very simple statement. So we've got this like defining statement here. So we are going to say that A is a subset of B. All right. So I'm sorry. A is an element of A, of the set A. So since by hypothesis we have A as a subset of B, and the definition of subset requires that A be an element of B. So we're just kind of like, you're walking the reader through the definition. So you're just saying, hey, if A is an element of A and A is a subset of B, then by definition, A has to be an element of B. Similarly, since B is a subset of C and A was an element of B, and A must be an element of C, therefore, we've proved that A is a subset of C. That's straightforward. So the trick to these is just like really understanding like what's good enough to prove that we've gotten there. And that kind of goes back to those statements about, it's like, this is just a framework of the overall argument, but this gets us through that idea that we can like reason our way the rationale as to how to prove something. Proof by contradiction, on the other hand, is we're going to go back and think about some stuff we did in with negation. And so note that the negation that we had like from chapter 1 is if P then Q, the equivalent to that is P and not Q. So remember that the notation for that would be if P then Q. And if we negated that, then that gave us the logical equivalence that it was P and not Q. And so that was just one of our logical equivalent statements that we had. So this is basis of the proof of contradiction. In a proof of contradiction of a theorem, the form if P then Q, we first assume the negation. So we're going to assume. So even though we know that we have an if P then Q, we're going to assume the negation is true. Then show that it leads to a contradiction. Thus, the negation of the theorem will be false and the theorem is true. So it's like a backwards way of like getting to the answer. It's like you're going to like assume negation to show that that's false because that's a counterexample. And so if that's false, then that means that the if-then statement is going to be true. It's like, or not the if-then, but the theorem itself is true. So it's kind of a convoluted way to get there, but it works. All right, so we use that with this particular one for an integer n. If n squared is even, then n is even. So once again, our preparation for this is like going through and kind of thinking about in our head, like remembering like, oh yeah, remember like 16, 64, and 112. So those are all even numbers. If I square them, so 16 is 4 squared, 64 is 8 squared, and 12 squared is 144. And so if we get this idea that we are kind of modeling this, what we're saying here is because what we're really trying to get to is that n squared applies n, right? So it's like this idea that if this guy is even, then this will be even. And so we're kind of modeling that here to kind of let ourselves see. So in previous theorems, and we didn't actually do theorem 5, so it's one of the things you might want to go back and take a look at. I'm not requiring that of you. Some of your homework problems in section 3.1 will require you to do some of the past theorems, or some like there's like 12 of them, or not 12, like 5 of them, I think. But yeah, so you go back and do some of those, and kind of look at that. But now we know we can apply this. So even though we didn't prove it, somebody else has. So now we can use that, and that is theorem 5 says if x and y are odd, then xy is odd, and the product of xy is odd. So our reflection is, since we proved the theorem by contradiction, we'll start by assuming P and not Q. And so we'll get there in just a second and see what that's going to look like. So we'd say, suppose an integer n squared is even, and n is not odd, right? Or n is odd, excuse me, not odd. N is odd. So that's the negation of that. So let's take a look at what happens here. All right, so we're going to suppose the negation. Suppose n squared, I forgot to put that as a squared, sorry, is even, and n is odd. By theorem 5, since n is odd, then n squared, or nn, is odd. So we're using something that was already proved to show us. This is a contradiction to the fact that n squared is even. And I apologize once again, I didn't get that superscript put up there. I'll get that fixed when I post this for you. This is a contradiction to the fact that n squared is even. Hence, our assumption that n squared is even and n is odd is false, making our theorem true. And that wraps up 3.2. Some of the homework in this section is going to be tied to, just kind of applying like definitions. Some of them be start to form proofs. Please reach out if you have any questions.